AI agents are really popping up everywhere these days, aren't they? You see them as intelligent coding assistants helping debug complex systems, or these advanced search tools digging through just massive amounts of data. But here's the thing, the persistent challenge, really a massive hurdle, has been how do we effectively train these agents?
Right.
How do we make them truly adaptive, consistently reliable, especially out in the dynamic, often unpredictable real world? Because traditional reinforcement learning, RL methods for large language models, the LLMs, they've often felt a bit short. They can be rigid, often designed for simpler single-turn tasks, and they usually demand that the agents themselves are either completely rebuilt or, heavily modified just to fit into the training setup. So imagine this. What if you could take any AI agent you might already have, maybe one built with popular tools like LangChain or AutoGen, and train it using advanced RL, and do it with almost zero code changes?
Right, that's the promise.
That's exactly what Agent Lightning, this groundbreaking framework from Microsoft Research, is aiming for. Their core idea, the real innovation, seems to be this complete decoupling of the agent's execution from the actual RL training process.
Exactly.
So how does it work? Well, it starts by defining agent execution formally as a Markov decision process, an MDP. Then it creates this unified data interface to capture all the interactions as training trajectories. And it uses a sophisticated hierarchical RL algorithm called Lightning RL. And the results look pretty compelling. They've shown it's effective across diverse, complex tasks, things like text-to-SQL, retrieval augmented generation, RAG, even tricky math problems needing tool use. It seems to deliver stable, continuous performance improvement.
Yeah, the consistency is notable.
So this deep dive is really about understanding how Agent Lightning might just open the door to truly adaptive, self-improving AI agents, making this advanced RL training practical and accessible for real-world stuff. Welcome back to the deep dive. Today, we're tackling a really critical challenge right at the cutting edge of AI. How do we get AI agents to move beyond just being smart to being truly adaptive, capable of continuous learning out there in the wild? We've all seen how incredibly capable these LLMs are, but you put them in the real world with all its messiness, multi-turn chats, private data, unfamiliar tools, and they can sometimes, stumble.
They can.
And that's precisely where effective training and fine-tuning become absolutely essential.
You really hit the nail on the head. I mean, think about an LLM acting as a sophisticated agent trying to solve some complex interactive problem. Your traditional supervised learning, it often just doesn't cut it.
Right, the labeled data problem.
Exactly. That approach needs tons of painstakingly annotated step-by-step data, which just isn't scalable for these really dynamic interactive tasks. And that's where reinforcement learning, RL, really starts to shine. It lets models learn from these outcome-based reward signals, kind of like how we humans pick up skills through trial and error. It's all about enabling these models to figure out desirable behaviors directly from the feedback they get from their environment, turning those text tokens the LLM generates into actual meaningful actions in the world.
Okay, so RL sounds like the perfect fit, right? Learning by doing.
Yeah.
But the paper makes it clear it hasn't been easy applying RL to agents. What exactly makes it so hard right now?
Well, the main difficulty really comes down to the inherent complexity and, honestly, the sheer diversity of these agents. Most of the existing RL methods for LLMs, they're largely built for static sort of single call situations. Think like answering a straightforward question in one shot. But agents, they're way more involved. They usually need multiple LLM calls, one after the other. They're interacting with all sorts of external tools, APIs, navigating these dynamic multi-step workflows. And all that complexity makes modeling their data and actually fine-tuning the LLMs at scale incredibly difficult if you're using traditional RL frameworks.
Gotcha. So if the old ways are too rigid, how does Agent Lightning get around this? You mentioned the complete decoupling between agent execution and RL training. That sounds like a pretty fundamental shift.
It absolutely is. It's a real game changer. If you picture it, you've got your user's customized agent, maybe built with LangChain or whatever.
Right, doing its thing.
Do its thing, interacting with its environment, generating all this rich interaction data, what the paper calls training trajectories. Agent Lightning then acts like this clever bridge or maybe an intermediary. It processes this data, standardizes it, and then feeds it efficiently into a dedicated reinforcement learning training engine. That engine takes the data, updates the underlying LLM, adjusts the parameters, and then those refined, updated models get fed back seamlessly to the agent via Agent Lightning. So you get this continuous learning loop.
That's neat. And what's really fascinating is how they pull off this decoupling. They formulate the agent's execution as a Markov decision process, an MDP. For those listening who might need a quick refresher, what does framing it as an MDP actually mean here?
Sure. So in an MDP, you define the core components of decision-making. For an agent, the state is like a snapshot of its execution at any given moment. This includes crucial bits of info they call semantic variables, things like maybe an internal step counter, the current values of important variables, or maybe the context of a resource the agent is using.
Okay, the current situation.
Exactly. Then the action isn't just, say, a single token prediction. It's the entire sequence of tokens generated by one call to the LLM, like a complete thought or instruction from the model.
A higher level action.
Precisely. And finally, you have the reward, which is just a number, a scalar signal, that tells you how good that action was or maybe how well the overall task is going. Having this structured MDP formulation is what lets them define this unified data interface.
A unified data interface. Okay, that sounds like it's tackling a real headache for developers. Sort of a standard format for all that potentially messy, different agent data. How does having a standard help?
That's exactly it. It lets them abstract away all the underlying complexities you get with different agent frameworks. It genuinely doesn't matter if your agent uses LangChain or the OpenAI agent's SDK or AutoGen. Its whole execution flow can be systematically broken down into this sequence of transitions, and each transition consistently packs the LLM's input, its output, and whatever reward signal is associated with it.
So no more custom data wrangling for every single agent setup.
Pretty much. It standardizes the training data pipeline.
Let's make this really concrete. The paper uses a retrieve augmented generation, or RAG agent as an example. Can you walk us through how that RAG agent works with this unified data interface?
Yeah, definitely. So imagine an RAG agent. Its job is to answer a user's question by looking up info. First, the user asks something, input comes in. Then the LLM acts. Its action is generating a search query based on the user's question. That's our first call, or high-level action.
Okay.
Next, maybe a separate search tool uses that query to fetch some relevant documents or passages. Now, this is a tool call, not the LLM directly, but it's a crucial step in the agent's process.
Right, part of the workflow.
Exactly.
Yeah.
Then finally, the LLM acts again. This time, its job is to synthesize an answer using both the documents it got back and the original user question. That's a second distinct LLM call. And throughout this whole process, the state, remember those semantic variables like the user input, the query generated, the passages found, the answer being billed, it keeps evolving. The unified data interface meticulously captures each of these steps, these transitions. It includes the outputs from non-LLM parts too, like that search tool result. And crucially, it captures the reward, which, as you know, often only comes right at the very end when you see if the final answer was good or not. It's this clean abstraction, this consistent format that really enables the decoupling Agent Lightning provides.
Okay, that makes sense. So we've got this nicely structured data flowing thanks to the MDP view. Now, how does Agent Lightning actually learn from that data? That's where Lightning RL, their hierarchical RL algorithm, comes in, right?
You got it. Most of the RL algorithms you see for LLMs today are built for what we call single-turn interactions. The LLM gets a prompt, generates a response, and you optimize that maybe token by token.
Right.
Agent Lightning takes a step back, a higher level view. Instead of treating every single token as an action to optimize, Lightning RL treats the entire block of text generated during one LLM invocation as a single discrete action. And this is key because a complex agent task might need the LLM to take several of these high-level actions in sequence.
So it's like optimizing the LLM's contribution at a more strategic point in the agent's overall plan, not just tweaking individual words.
That's a great way to put it, exactly. It uses this neat two-step mechanism. First, it takes the overall reward for the whole task, did the agent succeed or fail in the end, and it assigns that value back across all the individual actions, all the LLM calls that happen during that task. They call this the credit assignment module. Now, currently, they use a fairly simple method for this, basically giving the same credit to all actions within that task.
Okay, simple but effective for now.
Right. Then, existing single-turn RL algorithms, the ones that are good at token-level optimization, handle the second step. They take the credit assigned to each high-level action and figure out how to distribute that credit across the actual tokens within that specific action's output.
So it leverages existing techniques for the fine-grained part. What are the big wins with this hierarchical approach? Sounds pretty flexible.
Yeah, there are several really compelling benefits. First off, it lets you plug in basically any existing single-turn RL algorithm without having to change it. That massively simplifies the whole training setup.
That's huge for practicality.
It really is. Second, it allows for incredibly flexible ways to construct the observation, for the policy, basically, the input the LLM sees before each call. This input can be dynamically put together from the agent's current state. Maybe it's a short summary of what happened before, maybe it's a very structured prompt, or maybe it's just an instruction telling the LLM what role it needs to play right now.
And is this approach more robust than some of those masking strategies people have tried? I remember reading about those.
Oh, absolutely. Those previous methods often involve just concatenating everything together, all the turns in a conversation or task, into one huge input, and then using complex masking to tell the LLM which parts to pay attention to or update.
Sounds messy.
It can be. It creates this really tight coupling between the training and the agent logic. It can mess up token continuity, which matters for things like positional embeddings, how the LLM understands word order.
Right, like ropey embeddings rely on that.
Exactly. And it just adds a ton of debugging headaches. Lightning RL completely avoids that by breaking the whole thing down into these individual transitions. It aligns much more naturally with how LLMs actually process input, making implementation and scaling way easier. It also neatly sidesteps that accumulative context issue, where the input just gets longer and longer and longer, potentially overwhelming the LLM or your training resources.
Okay, this next bit seems really critical for developers listening. Beyond the algorithm, how did they actually build the system architecture to work smoothly with all these different agent frameworks? The paper talks about a training agent disaggregation architecture.
Yeah, this architecture is, I think, a fundamental breakthrough for actually using this stuff in practice. It completely separates the really heavy lifting, the LLM generation and the training, which needs beefy GPU servers, from the much lighter, more flexible application logic and tool interactions, which can be written in standard languages like Python. So you have the RL framework running on its servers, focusing only on optimizing the LLM, and it exposes a clean API, actually quite similar to the OpenAI API that many are used to.
Okay, familiar interface.
Right. And then the agent itself, maybe running on a client machine or a less powerful server, just interacts with this API. It manages its own workflow, its own tool calls, completely separate from the training mechanics.
So the training system doesn't need to know the agent's internal details, and the agent doesn't need to know how the training works. Agent agnostic and trainer agnostic. That sounds incredibly flexible.
That's precisely the goal, and it seems that they've achieved it. The training framework doesn't need to understand the agent's specific step-by-step logic, and maybe even more importantly, the agent doesn't care about the training framework's implementation details. This is a massive win because it removes that barrier, that often painful need to completely rebuild or heavily twist your existing agent just to make it trainable with the new RL system. Developers can stick with frameworks they know, like LangChain or AutoGen, without these huge migration efforts.
Can you tell us a bit more about that client-side agent runtime? It sounds like it's doing quite a bit of work behind the scenes.
It is, yeah. The agent lightning client is actually pretty sophisticated. It handles things like data parallelism, so you can run multiple instances of your agent at the same time to process big batches of tasks, either on one machine or spread across many. It's designed to capture all the data needed for training without you having to modify your agent's code. It often uses standard tools for this, like OpenTelemetry for tracing.
OpenTelemetry, yeah, for observability.
Exactly. So it watches how the components interact. And crucially, it has robust error handling built in. It can detect if an agent crashes or if a tool call just hangs forever, retry tasks that fail, and generally make sure the whole training process remains stable, which is often a challenge in complex systems.
And I saw something called Automatic Intermediate Rewarding, AIR. That sounds really handy, especially for those tasks where you only get feedback right at the very end, sparse rewards.
It's super useful. You're right. In many complex, multi-step scenarios, the only clear reward signal is final success or failure. AIR cleverly converts system monitoring data, like did a specific tool call succeed or fail, into intermediate reward signals. This gives the agent much more frequent, more granular feedback while it's learning, which can significantly speed up and improve the learning process. And what's cool is that developers can even customize these intermediate rewards to nudge the agent's behavior in specific ways.
Okay, so all this technical innovation, the decoupling, the MDP, Lightning RL, the architecture, it sounds impressive. But does it actually work in practice? What does this mean for someone actually trying to optimize their agent?
The paper tested Agent Lightning on 3 quite different challenging tasks.
It does seem to work, and the results reported are pretty compelling. They show stable and continuous performance improvement across the board. First, they looked at Text-to-SQL using LangChain on the Spider dataset. You know Spider, it's known for really complex database queries.
Yeah, it's a tough benchmark. Definitely. And here it was actually a multi-agent setup where one LLM was prompted to act as 3 different specialist agents, a SQL writer, a checker, and then a rewriter. Agent Lightning successfully optimized 2 of these agents at the same time. This really showed its ability to handle these complex, multi-step decision flows and even selectively optimize specific parts within a larger multi-agent system.
Wow, okay. So coordinating multiple roles for one LLM and training them selectively, that's impressive.
It is. Then second, they tackled Retrieval Augmented Generation, or AG, using the OpenAI agent's SDK. This was on the music dataset, using Wikipedia as the knowledge source, so very open-ended question answering. Here, the LLM had to figure out good search queries, retrieve documents, and then put together an answer. Agent Lightning showed stable improvement in both query formulation, getting better at asking the right questions, and in reasoning over all that retrieved text.
And what about tasks needing precise interaction with external tools, like a calculator? That seems like another common agent pattern.
Good point. That was the third task. Math QA with tool usage, this time via AutoGen, using the CalcX dataset. Here, the agent absolutely had to call a calculator tool accurately for intermediate steps to solve math problems. Agent Lightning proved really effective in these settings that demand precise external function calls meshed with internal reasoning. Getting LLMs to use tools reliably is often tricky.
Looking at those results across different frameworks, different types of tasks, what stands out most to you?
Honestly, the consistency. It's one thing to show improvement on one specific setup, but to see it deliver stable gains across different agent frameworks, LangChain, OpenAI SDK, AutoGen, different kinds of task complexity, SQL, R8, math, and even in multi-agent scenarios. That's pretty compelling. It wasn't just marginal improvement either, it was consistent upward trends. That really validates the flexibility of the approach and its potential for making a real difference in practical agent optimization.
So stepping back a bit, this deep dive really suggests a significant step forward. How do you see Agent Lightning fitting into the bigger picture, the broader landscape of AI agent research and development? What's its ultimate significance?
Well, if you look at the trajectory, I think it fundamentally changes how we can approach training these agents. A lot of the existing ways to handle multi-turn RL, as we discussed, use these somewhat cumbersome concatenation and masking tricks that inherently ties the training mechanics very tightly to the specific way the agent is built. Agent Lightning, with its transition-based modeling and that clean decoupling, just elegantly sidesteps that whole issue. It means it can support a much wider range of agent designs and workflows. It also helps with that long context headache by breaking things down naturally. So essentially, it flips the burden. Instead of developers having to bend over backwards to adapt their agents to fit some rigid training framework, we now have a system that adapts to their agents however they're built.
That's a powerful shift. It's not just about getting slightly better training results, but about making advanced training genuinely practical and accessible for almost any agent project. Looking ahead, what exciting new research directions or maybe practical applications do you see this kind of framework enabling?
Oh, it really opens up quite a few interesting avenues. The researchers themselves mention integrating even more optimization techniques beyond just RL, for instance. Could you use this framework for automatic prompt optimization? Maybe treat the prompt generation itself as just another component of interest to be optimized.
Interesting idea.
Yeah. And there's always room to develop more sophisticated RL algorithms specifically for agent challenges, like better long horizon credit assignment, figuring out which action way back actually led to the final success, or smarter ways for agents to explore their environment. And of course, further improvements on the infrastructure side, perhaps even more cleanly separating the trainer, the inference engine, and the agent's workflow, could unlock even greater scale and efficiency for really complex, demanding real-world applications.
Well, our deep dive into Agent Lightning certainly highlights how a really clever architectural approach combined with that hierarchical RL strategy can break down some major barriers we faced in training truly adaptive AI agents. It feels like a very powerful step towards making these LLM-powered systems genuinely learnable, responsive to the messy, dynamic real world, crucially, without forcing developers to completely rewrite their existing agent code bases.
It really does. And it leaves us with a fascinating question to ponder, doesn't it? By breaking down these traditional walls between how we build agents and how we train them using advanced learning techniques, how might this kind of decoupling unlock entirely new kinds of adaptive AI systems? Systems perhaps that we haven't even conceived of yet.